Hello, so today I will be describing the fourth problem on exam 2 for modern physics. So question we have is, for a particle with energy E less than U naught incident, potential energy step, show that psi naught and psi 1 from the equations listed below that are given, with solutions to the Schrodinger equation in two regions, x less than 0 and greater than 0. We also have to find the constants B and D in terms of A, applying boundary conditions at x equals 0. So the given equations are here. And what we'll do first is we're going to recall Schrodinger's equation here. This is just given. And I drew the potential step here to describe what a potential step is. So what it is at x equals 0, there's a jump from v equals 0 to v equals u naught. And we'll call these regions psi naught and psi 1, where those will be the functions in those regions. And x goes from minus infinity to infinity with that step at x equals 0. So in the region of psi naught for x less than 0, it's given above that psi naught is a sine k naught x plus b cosine k naught x, with k naught is equal to square root of 2me over h bar squared. What we'll do is we'll plug this into Schrodinger's equation and prove that the left-hand side and right-hand side are equal. So first things first, we have the constant. This doesn't change, minus h bar squared over 2m. We have to take the second derivative with respect to x of psi. So it's essentially the same function, but with negative constant squared. It's inside of the sine and cosine terms. The reason this is because if we take the derivative of sine, we get k naught cosine. Take the derivative of k naught cosine, we get minus k naught squared sine. So that's where we get minus a k naught squared sine k naught x. And it's the same deal with cosine. So we'll have minus b k naught squared cosine k naught x. And I added the plus 0 here to represent that is what v of x is in region 0. So that's before the step. And then on the right-hand side, it's just e times psi, which is a sine k naught x plus b cosine k naught x. Essentially what we'll do next is we're going to factor out psi from both sides. On the right-hand side, we already have psi factored out. We don't have to worry about that. On the left-hand side, factor out psi, which is given a sine k naught x plus b cosine k naught x. And then that's factored out, and we have left is minus k naught squared, as you can see from this line above. And essentially what we'll do is we'll cancel psi from both sides. And what we're left with is minus h bar squared over 2m. That never changed. This term here, minus 2me over h bar squared, comes from the fact that k naught is the square root of 2me over h bar squared. And we have this minus k naught squared term here. So we're going to square this, get rid of the square root. That leaves us with minus 2me over h bar squared. And psi was canceled on the right-hand side. So we're just left with e on the right-hand side. Now, it's pretty straightforward. Cancel 2m here. We cancel h bar squared. We cancel a negative sign. We're left with e equals e. So that proves that in region 0, this is a solution to Schrodinger's equation. Now we have to do the same process for x is greater than 0. And essentially what we're given is that psi 1, the psi in the region 1, c e to the k1x plus d e to the minus k1x, that's given above here, as well as k1 is the square root of 2m over h bar squared times the quantity u naught minus e. Same process, plug this into Schrodinger's equation. So first things first, the second derivative of psi is going to be the same function, but with the constant squared pulled out front. That's because e to the k1x, take the derivative of that, that is k1 e to the k1x, and take the derivative again, we get k1 squared e to the k1x. So that's where in minus h bar squared over 2m, doesn't go anywhere. Second derivative of psi, we get ck1 squared e to the k1x plus dk1 squared e to the minus k1x. And then we're going to add v times psi. And we know that v in region 1 is u naught. And here's the psi equation given above here. We set that equal to e times psi on the right-hand side. And we'll do the same thing we did last time, and we'll factor out psi. So c e to the k1x plus d e to the minus k1x. You could factor that out from both sides. So we factored on the right side, so we don't have to worry about that. On the left-hand side, we can see that once we factor that out, we're left with a k1 squared term times minus h bar squared over 2m. That's this right here. And we're also left with u naught. We factored it from u naught as well. So we can cancel psi from both sides. That'll leave us with minus h bar squared over 2m. And I get this term from the fact that k1 is the square root of 2m h bar squared times u naught minus e. We take the square root away since we're squaring it, and we're left with this right here. And obviously we keep the u naught. And now we'll just cancel things out. 2m cancels, minus h bar squared cancels. The minus gets distributed out, so we have positive e minus u naught plus u naught, which is this here, is equal to e. U naughts cancel, and e is equal to e, so that proves it. This is a solution for region 1 for the Schrodinger's equation. And the next part of the question is asking us to find constants b and d in terms of a. So we know boundary conditions at psi naught of 0 at x equals 0 has to be the same as psi 1 at x equals 0. And also the change, the derivative, also has to be the same for psi naught and psi 1. What we'll do is we'll take what our psi naught equation was. So our psi naught equation was right here. At psi naught of 0, the cosine term goes to 1, sine term goes to 0, we're left with b. So we'll have psi naught of 0 is equal to b. We do the same thing for psi 1 of 0. So if we look at psi 1, we plug in 0 for x, e terms go to 1, so we're left with c plus d. So so psi 1 of 0 is equal to c plus d. We know this have to be equal because of the boundary conditions. Therefore, b is equal to c plus d, and that's going to be our first equation. And the other boundary conditions are the derivatives are equal at x equals 0. So to take derivatives of the function, which are pretty straightforward. So we have a k naught cosine k naught x minus b k naught sine k naught x. This is negative because we had a cosine. This is positive because we had a sine. And now we have to plug in x equals 0 for these. We know the cosine term will go to 1, sine term will go to 0. So we're left with a k naught. And we have to do the same thing for psi 1. So psi 1, a derivative of psi 1 is c k1 e to the k1x minus d k1 e to the minus k1x. And what we'll do is we'll plug in x equals 0 again to get psi 1 prime at 0. And so we know that the e terms will go to 1, so it'd be ck1 minus dk1. And that gives us the second equation here because we know that psi naught and psi 1 have to be equal. Their derivatives have to be equal at x equals 0. So we have a k naught is equal to ck1 minus dk1. That's our second equation. Now, since the c e to the k1x term in the psi 1 equation represents Schrodinger's equation moving to the right, we have to keep it constant at infinity, x equals infinity. C has to be 0. If c isn't 0, then this Schrodinger's equation won't be constant at x equals infinity. So then for equations 1 and 2, we can just set c equal to 0. So that we're calling equation 1 and 2. We have b equals d, and a k naught is equal to minus dk1. Now, expanding equation 2, we can divide both sides by k1 and -1. You get negative a k naught over k1 is equal to d. We also know d is equal to b, so that's why I put that there. And simplify or putting k naught and k1 in from above, we know that k naught is equal to this quantity and k1 is equal to this quantity here. Now, when you have square roots dividing each other, you can basically treat it as one big square root. So I can cancel the 2 m's. I can cancel the h bar squared. And we'll be left with e divided by u naught minus e right here. So final term, b equals d is equal to minus a times the square root of e divided by u minus e. So that is problem 4 for the Modern Physics exam 2. Thank you.